Thank you very much. Eric Ward does that so well, doesn't he? It's just great. Well, welcome to the 22nd annual Paul D. Bartlett Senior Lecture. This is just so exciting to be here, and I will say it's exciting to be my second one. So I've just been here a little over a year. And I'd really like to extend a very warm welcome to the library trustees, the President's Circle members, and our distinguished guests, and our live stream viewers tonight. The Paul D. Bartlett Senior Lecture is named for the very first chairman of the Linda Hall Library Board of Trustees. In 2003, the library launched the Bartlett Lecture in conjunction with the Kansas City-based alumni associations of Harvard, Yale, and Princeton. And together, as many of you know, because you've been here quite a number of times, I'm sure, we brought distinguished professors from these prestigious universities to the Linda Hall Library to speak about the many ways in which science impacts the world we live in. So I'd first like to acknowledge Jim Hebenstreet and Marilyn Bartlett Hebenstreet for their ongoing support of the Bartlett Lecture Series over the last 2 decades. Thank you so much for this. I'd also like to recognize John Goodwin of the Princeton Alumni Association of the Greater Kansas City for his help in presenting tonight's speaker. So thank you, John. Wherever you are, somewhere, thank you. John, along with Dwight Arnn from the Yale Club of Kansas City and Jessica Kerrigan from the Harvard Radcliffe Club of Kansas City, have recently stepped down from the Bartlett Lecture Planning Committee after many years of service. And it's just been great working with them, and really, really so grateful for your contributions. Thank you for your great work in making this our signature event every year. So now it is a great pleasure to introduce the very interesting and delightful Dr. Sigrid Adriaenssens. Did I get it? Signature, great. Adriaenssens. She's professor of civil and environmental engineering at Princeton University. She's director of the Form Finding Lab at Princeton. Her research focuses on lightweight service systems and how they can be optimized and realized to interact with extreme structural or environmental loading. The applications range from adaptive building shading devices to large-scale inflatable storm surge barriers, and are sometimes inspired by systems that evolved in biology, art, or architecture. She earned a bachelor's, master's, and doctorate in civil and structural engineering from the University of Bath in the United Kingdom. Please help me welcome Dr. Sigrid Adriaenssens.
Thank you. Thank you so much. All right. Okay, well, thank you so much for having me here tonight. It's a real pleasure. It was Louis Burgess who said, I imagine paradise to be something like a library. And I'm an engineer, so I'm kind of in my little paradise here. I'm also very delighted to be presenting in this series because I learned from Eric that my former colleague, Professor David Billington, was one of the first people to give that lecture. So I'm very honored also in that way to kind of be succeeding him, somehow a couple of years later, but that also makes me very happy. And as some of you know, I love Kansas City as well. So, okay, let me figure out, they explain this to me. No, this one. Yeah, so I moved with my family about 15 years from Belgium to the United States to New Jersey, because Princeton is in New Jersey. And we like to go in the weekend to the Jersey Shore. And so, yeah, we do. And when we drive on, this is Highway 1, this is a picture I've taken, I am always kind of surprised to see these kind of bridges. They are very massive, there is a lot of material in there, and that, when I know that the construction industry is one of the most resource-intensive industries, And if there are any mechanical or civil or structural engineers amongst you, you know that if you actually model that bridge as just two beams, simply supported beams, these are really the shapes that these bridges should have. And if you do that, you save about 30% of materials, which is great for the economy, for the client, but it's also great for the environment. And then, when we get to the Jersey Shore, and actually this is not a picture of the Jersey Shore, this is Rockaway Peninsula in New York City, but you notice that there are a lot of people enjoying the seaside, and that is also a global phenomenon, that people are moving to urban centers, and that people are actually moving. Many of these urban centers are at places where there is the water. And then, unfortunately, in 2012, this is what happened. This is Hurricane Sandy, and of course, this is extremely topical because today we have Hurricane Helene, approaching Florida. So this happened in 2012 in New Jersey. And this is not a rendering. This is not a kind of AI-produced picture. This is a picture. This is a real picture of the kind of damage that this hurricane produced in 2012 in New Jersey. So there was huge billions amounts of economic damage. 650,000 homes were destroyed, and of course there was also a lot of human loss. And we know that these hurricanes are going to be more frequent and more intense. And so I, as a civil engineer, was very shocked when I was afterwards seeing images like this, where basically all these coastal communities were in a hurry to get their boardwalks back up exactly in the same way as it was before. And of course, this is a disaster waiting to happen again. Some other communities took more proactive approaches, like for example, this is Brick, New Jersey, where they actually built a big seawall. So the idea is here, if you build a big, massive wall of stones, then that wall will kind of stop the storm surges. Yes, it might, but also, you cannot actually go on the beach anymore. Your real estate property goes down, and animals cannot really move, between the land and the water anymore. So I don't think this is a really good solution either. So in my research, I look at what is the relationship between form and efficiency in structures. And we kind of develop methods, and we use mechanics and design to kind of transform the engineering design framework from thinking about just using a lot of materials and using mass to a more lightweight, forced modeled framework, and hopefully this will contribute to our quality of life. I am not the first one to think about using form, because my lab is called the Form Finding Lab, forms rather than mass to span large systems. If you look here on the x-axis, you have time. If you look on the y-axis, you have weight. Note that that's a logarithmic scale, so it's not 1, 2, 3, but it's 0.1, 1, 10, 100,000. And you might recognize some buildings on there. On the top, the very bad ones are the pyramids, right? They're very massive. But as you go down through time, you have the Pantheon, you have the Gothic cathedrals, and then if you go all the way to the right, you have some shell structures. Actually, you have number 14 is a building that I worked on, which is very lightweight structures. Actually, we can build structures now that they are so lightweight, so they use so little materials that if you design them wrongly and a strong wind comes, they will lift them up. So you have to design them properly so that doesn't happen. But so I'm not the first one who thinks using form rather than mass is a good idea. And this is really necessary because our world is facing, and especially like the construction industry, some acute challenges. The first one is, of course, climate change. Oh, okay. What does that mean? I just keep on going? Okay, keep on going. All right. So climate change. So the construction industry is responsible for 30% of the CO2 emissions. And actually, I was just talking about that with somebody here in the audience. So in China, actually, they imposed, in 2017, they imposed a 4-month construction ban, like no more cement being made because it was just too much pollution. Then, I don't know if you know this, but actually, for example, if you use concrete, one of the ingredients of concrete is sand, which is a non-renewable resource. Today, we use about 10 billions of tons of concrete a year. In 2060, it will be 60 billion tons of concrete. We actually don't have enough sand to make all that concrete, right? So we're depleting completely non-renewable resources. And then finally, when we make things, or buildings and bridges, we produce, in the US, 29% of the landfill is actually coming from a construction site. And then we are dealing with extreme loading. Some of these loads have always been there, like earthquakes and things like that, but some of these loads are becoming like the storm surge loading. You know, these storms are going to be more frequent and more intense, and so these extreme loads are loads that, you know, don't occur very often, but when they occur, they really peak in their loading conditions. And then there are some challenges of all times. The first one is the rail that I work in is scale. So, you know, you have all kinds of different engineering, but, you know, you can design iPhones, you know, quite small. But if you're in civil or structural engineering, you design things in the range of 10 to 100 meters, or maybe 1 kilometer or 10 kilometers. So we work at a very large scale, in terms of space, but also in terms of time. We want the things that we design and build to last more than 2 years or 5 years. We design them for 50 years, 100 years, but sometimes they last 400 years or 2,000 years. So that's also a challenge. And also in terms of materials, we do not have such a wide palette of materials available. And I was very happy today when Eric showed me one of their newest acquisitions here in the library is a book by Galileo Galilei. And actually, he's one of my heroes because he kind of described that you cannot just take something that works at the small scale and then scale it up. That is because area kind of squares to the power 2, but volume squares to the power 3. And so if you take a bone of an animal and you think, oh, I'll just make that structure a little bit bigger, actually that bone would look like that. So you can't just take something small and make it bigger. It doesn't work in terms of scale. I'm going to come back to this. This one is one of my favorite structures. This is the dome in Florence. And I'm showing it here because, of course, this dome has to carry itself weight, but also already for 600 years, it has been resisting seismic loads, right? So we have to design our structures for a long time. And then also, in terms of materials, I mentioned this, as you will see today, I'm a lot inspired by nature, but nature has a very wide palette of materials available. In buildings and bridges, we don't have such a wide palette available. So that's another challenge. So I think we need to change what we design, how we design, and how we build it. And so my idea is to use slender surfaces. So you will see my talk. I will talk about shells, rigid shells, flexible shells, membrane structures. I think we should use geometry and mechanics. This is actually very complicated because we are working here with nonlinear behavior. We're working with large strains, large displacements. And then also, I think we should build using waste-free processes. We want to get rid of that 29% of construction waste in the landfill. And actually, the American Academy of Engineering states this as one of the big challenges, right? That we should try to build, more carefully and maybe draw inspiration from computer science, and I'm going to talk about that. So my proposal is to kind of leverage the extraordinary mechanics of these, what I call slender surfaces, of very thin surfaces that have one dimension that's much thinner than all the other dimensions, and these kind of surfaces behave amazingly because they are what we call indeterminate. They spread their forces throughout the surface. So if there's somewhere a hole, the loads can find a path somewhere else. They have properties that normal structures like beam and column structures don't really have. And they behave non-linearly, even if their materials are behaving linearly. And so I'm going to show you examples of how we can use flexible shells that change their shape, how through folds and corrugations we can actually give an object a higher load-bearing capacity. I'm going to show you a process how you can build without creating waste. And I'm also going to come back to the storm surge barriers and talk about how we can tune their stiffness. So this is my proposal, and I'm going to talk about this last, which is absolutely relevant today when we're talking about Hurricane Elaine. So instead of building these kind of permanent concrete or stone walls, I'm proposing an inflatable membrane that can be filled with water and that is going to resist extreme loading. This is a rendering, by the way. This is not a real picture. I'm going to talk about how can we shape shells for large span systems so they can keep people safe from seismic events? How can we construct efficiently without creating waste? And I'm going to start with this one. How can we design buildings that keep us comfortable while also reducing energy consumption? And this, again, this is a rendering for an imaginary museum in Marfa, Texas. So I'm going to start with this one here. So I'm interested in what they call adaptive facades. So these are facades that can adjust their aperture to lighting conditions or heating conditions outside. This is not a new concept. For example, in Paris, in the Institut du Monde Arabe, they have these kind of adaptive facade elements, but often they're rigid body motions. That means that they have rigid parts and hinges, and often they fail. If you go to the Institut du Monde Arabe, you actually see it doesn't move anymore. It's kind of stuck. But it has been shown that, if you do that, so this is the same museum, but maybe at twilight, you want your facade to be completely open. And maybe at noon, when, there's a high lighting levels, you want your facade to be closed. So it has been shown that if you can make such an adaptive facade, you can save up to 40% of building energy, that goes into lighting, heating, and cooling. And so we started looking at plants for inspiration. Now, you might think that plants don't really move. If you think about a cactus, that doesn't really seem to move. But if you think about a sunflower or a Venus flytrap, that obviously move. Plants move to protect their organs, to catch prey, as you see here, or to pollinate. And so we're interested in seeing, is there something that we can learn from plants? Because plants do not work with rigid parts and hinges. Everything is kind of elastic and deforms. Is there something there that can cause repeatable movements and that we can scale up to the kind of facade level? So we worked with a biologist, Sasha Eisenham, and we identified in the plant world 5 different types of ways that plants move. The first one is differential expansion. So basically, as if you have 2 layers of cells, and in one layer of the cells, the pressure gets higher, then this thing starts curving. The second one is torsional buckling. This is the bird of paradise flower. It has like a very slender element sticking out. If a bird sits in that, then the flower, that thing kind of twists, and the flower deposits seeds on the bird. Another way is using layered material anisotropies. So basically, that is if you have 2 materials that have a specific fiber orientation, if you put them together, and then, for example, you put humidity, these things will kind of want to work against each other, and you can get all this warping. Then there is release of elastic energy. That's mostly in the dissipation of seeds. But we were most interested in shell geometries and mechanics. Because what we see there is that we see things deforming elastically, mostly in bending, not in stretching. If you stretch something, that requires a lot of energy. Now, nature is very smart and very lazy. It doesn't want to dispense a lot of energy, and it doesn't want to create a lot of materials either. So nature is kind of of a perfect teacher in that way. So we were interested in those kind of plans, but not in the Venus flytrap, because that one, if you imagine that on your facade, it would just be open, close, open, close. That would not be very pleasant to be in, but we found another flower, this one here, which actually grows in Australia, is the Stylidium graminiifolium, and you see it on the left-hand side. It basically has this kind of curved thing, and you see on the left-hand side the red bend, that is the active bend, and basically if a bird comes and sits there, it kind of hits the bird and deposits seeds on it. So the red part, so we were interested in the red part because that causes a great movement, and actually that red part is what you see there in the middle. It's actually the same geometry if you cut a Coke bottle open and you like split it. If you just move that a little bit, that thing will open a lot. We call that dynamic amplification. So we just actuate it a little bit and we get very large movement. And so we were thinking, can we use that kind of anticlastic curvature for a shading device? And you see our idea there on the right-hand side. So there on the right-hand side, the blue part is the active part. So if we squeeze that together or we shear it, then that red part will go open. And the way that we were imagining how this would be in real life would be we would have smart memory alloys there that would kind of contract both or one, and that would cause then this tongue to kind of lift or otherwise twist. And of course, we draw our inspiration from nature, but actually also Lord Rayleigh had already said before that when the shell is thin enough and it is vibrating in one of the graver possible modes, the middle surface behaves as if it were inextensible, so meaning no stretching, only bending. So what we did is we carried out analysis to identify eigenmodes, and these eigenmodes can show us how these shells will behave if we don't want them to stretch, but we want them to twist and rotate. And we call these isometries. And so these are the kind of geometries that we are interested in. We then looked at, what is the optimal ratio of both radii of curvature, and kind of established that so that this blue part, the active part, could do all the movement that we wanted to block out the sun. And so you see on the left-hand side, you see a finite element analysis. You see indeed the blue part, the kind of active part changing color, right? That's the active part that does all the movement, and then the blue part just kind of moves. And so with that geometry and the smart memory alloy actuators, we can have a facade that's closed, or we can bend it, then it just moves up, or we can shear it and then it twists. And so we can have a dynamic shading facade. And here is a rendering of what that would look like. So it's important when you design facades that people have a view outside. So this would allow a view outside. This is when it's fully open. This is when it's half open. And this is what it looks like when it's closed at the nighttime. So those are flexible shells. I'm now going to move to rigid shells, right? So things that don't really deform that much. The scale is 10 to 80 meters, and I'm kind of looking for things that might be useful for California, where many earthquakes happen. Now, if you look, if you do like a search on Google, you will see that many shells survive extreme events, right? So we have some examples here. Actually, the bottom middle one, that is in Florida, right? So all the houses are kind of around it are gone, but that dome still stands. Also here, this is after a tornado. And then there is, that is after a fire, earthquake. So shells seem to be very resilient under these kind of extreme events. And we wanted to check out why that is. So we started studying this beautiful church, which is in Mexico City, which survived the 1985 earthquake, which was scale 8, which was 8 on the scale of Richter. And so we kind of wanted to find out why this beautiful curved structure had not collapsed during the earthquake. And so we carried out dynamic statistical analysis to determine how this thing behaves when an earthquake hits. First of all, we kind of studied the stresses to make sure that it didn't break. It didn't really break. There is no kind of overloading. But the other thing that we identified is that it vibrates at a very high eigenfrequency. So that means like if you disturb it a little bit, it will start vibrating at a certain frequency. And for this kind of shell, it is actually very high. It's 3.09 hertz now. You probably don't know, but normally, like for example, in a building like this, the eigenfrequency of this building would be around 0.5 or 1. So it has very high eigenfrequency. This eigenfrequency is very different than the peak eigenfrequency from the Mexico earthquake, because that one is plotted there in black. It is for the earth. So the earthquake likes to vibrate at 0.5 hertz, while as the church wants to vibrate at 3.09 hertz. So these two frequencies are very far away from each other, so they do not overlap. If you have frequencies that overlap, they kind of make each other's worse, and you get a lot more damage. For example, this happened, I don't know if you remember, 2000, UK, they opened this beautiful Millennium Bridge. Everybody goes on the bridge, starts stepping in the same rhythm as the bridge likes to vibrate. This is extremely dangerous, because if you have the two together, this makes, this causes enormous stresses. So anyway, what we're seeing here, this is not going to happen. The frequency of the shell is much higher than the frequency of the earthquake, and that is because, I don't know if you know this formula, this is eigenfrequency, it is the square root of the stiffness divided by the mass. Now the mass of that church is very small because it's very thin. The stiffness is geometric stiffness. Because it is curved, it is very stiff. If something is flat, it's not very stiff. If you take a piece of paper, you let it hang, it will just flop down. If you curve it, or if your pizza, you curve it a little bit, it will not flop down. If you hold it like this, it will flop down, but if you curve it, it will not flop down. So if you curve something, it has enormous stiffness, and that is the reason why these shells behave so well under earthquake loading. So we kind of study how we can find shapes for these. So if we know that, we developed a technique to develop, in this case, an arch that would resist earthquake loading very well. We plot the thrust line, so basically that's the line where all the forces are going. The blue line is if it's just under self-weight. The green line is if we combine it with an earthquake. And of course, that was for an earthquake coming from right to left, but it can go the other way around. So we mirror image that thrust line, and we end up with an envelope. We then test that, whether an arch that looks like this would indeed resist an earthquake very well. We test it using virtual work, and indeed it can resist an earthquake very well. Now you might say, I've never seen an arch like this, or I have no idea how you would build that. That's true, but we have 3D printing. So, these kind of shapes now are completely possible. They were not possible when I was a student, but now they're completely possible. Okay, maybe we don't want to build arches, but actually maybe we want to build a gym, or we want to build a congregation area. So we can also, instead of taking the envelope, we can offset the second curve and then aloft the surface through it, and we end up with a geometry like the one that you see on the right-hand side. You might say, I've never seen anything like that either. Actually, it already exists. In 1978, Eladio Dieste, an amazing engineer from Uruguay, built these corrugated shells, very thin shells, to store grain. So not an iconic structure, just a very utilitarian structure. So our structure looks a little bit like that, except for that with us, the corrugations are offset. So with Eladio Dieste, they go all the way across, but with us, they're slightly offset. Our corrugations don't run over the entire thing. And so then we carried out what we call nonlinear pushover analysis. So we kind of push these geometries, not until the first crack occurs, but until we get a failure mechanism with 4 hinges. We produce many different variations of this, and we also test the Dieste shell, which you see at the bottom right. Now, what you're seeing is, when these shells are subjected to horizontal load, you see that eventually they fail. There is always 4, I have a pointer here, 4 hinges, right? So there is a hinge here, a hinge here, a hinge here, a hinge here, and we get that failure mode. But also what you see is that they fail differently. So sometimes you have A, B, and D, E, like also here and here. But sometimes you have a hinge here at the top. And it seems, so the failure mechanism is different. So, but it seems that So this one here, the one with the C, and also this one here, these are all the ones that have a corrugation depth, also here, this one here, a corrugation depth that's not very deep. And so why do these hinges form? That is because these hinges form in the areas where we have not curvature in two directions, but curvature in one direction. If you have single curvature, something is not so stiff, that will attract all the forces and it will break there first. So these are all the areas where we have single curvature, and that's where the hinges are occurring. And then if we study these different shells, we have the Dieste shell here. So how does that behave? Well, the first crack in the Dieste shell occurs at a 0.2 G, but a good earthquake is 0.3 G. So indeed, at 0.3 G, this shell, which is in Uruguay, is going to develop 4 hinges and will basically collapse. All the other ones outperform the first one. So everything is the same, span the same, height the same. Same amount of material. The only thing that is different are the corrugations. So we're just using form, not more material, to kind of generate all these different shells. And going back. And what we see, I keep on pressing the wrong button. What we see is that this one is really the best one, right? So this one, the first crack will start appearing at 0.35 G, and then really it collapses at 0.57 G. So this performance is much better than this performance here. Same span, same height, same amount of material. The only thing we're doing is we're playing with form. We're changing the corrugations, and because of that, we can actually give it a much better or much higher capacity. So here is a rendering of what this would look like actually in San Francisco. Now, people don't actually build shells anymore. Actually, they do build them as tornado shelters in the Midwest, but often people don't build them anymore because they're expensive to build. And why is that? Because this is a picture of one of the Felix Candela shells in Mexico. I don't remember from what time this is exactly, but this is from a time when materials were cheap, labor was cheap. This is not today United States, right? But what we see here is that in order to make this beautiful shell, you first have to build a wooden structure, also a beautiful wooden structure, but that, of course, all that wood goes into the waste film. And actually, it's estimated for these kind of projects that 40% of the shell project goes into the scaffolding and the formwork, so supporting it while it's being built, and then once the concrete is cured, you can take it away, and it often ends up in the landfill. So I'm going to show you now how we can build vaults and shells without creating any waste. And I'll put there equipment, humans, robots, AR. And I'm coming back to one of my favorite structures, right? So this is the dome in Florence. It dates back to the 15th century. As you might know, it was designed and built by Filippo Brunelleschi, who was a watchmaker and who won a design competition. And he claimed he could build this dome without using any scaffolding. Actually, it is now calculated that if he had used scaffolding and supports, he would have had to cut down all the forests in Tuscany to make the scaffolding. Of course, his clients didn't really believe, so he did have scaffolding to get the masons up there and to put the cranes up there, but the scaffolding was not supporting the dome while it was being constructed. So we were very intrigued because he did not write down how he did this. He worked with like a guild of masons. The Da Sangalo family was like a family that was building these kind of domes in northern Italy. And we have drawings like this one here on the left-hand side. So on the left-hand side, you see a plan view. So we see like radial bricks, and then we see some vertical bricks like spiraling up. On the right-hand side, you see a cross-section. You actually see it's a double dome. There's a dome on the inside, and then there are these yellow bricks that are connecting it to a dome on the outside. So basically, if you can build a dome on the inside, you can use that as scaffold for the dome on the outside. So we're interested on the inside dome, which has, in Italy, sometimes like single spiraling, and sometimes what you see there on the right-hand side, double spiraling spirals going up. Now, a lot of people think those are decorative. They're absolutely not decorative because often they're covered with plaster and with frescoes. So we started expecting that they must have something to do with the way that this dome could be constructed without supporting it during construction. So we started looking at this. We assumed we had a radial symmetry, that these domes would be like you build an igloo, would be built layer per layer per layer, and then eventually, you would kind of start going inwards, and that's where these things would start collapsing. We also assumed that these bricks, which are here colored in gray, would have something to do. And so basically, what happens is, of course, you start building your dome. You put, actually, I have to tell you, in order to calculate this, we carry out discrete element analysis, and we model every single brick. So we check one brick, what happens? We put another brick, what happens? So this is a very long process that we carried out. But what we discovered, so you find you're building your dome. Initially, it's fine. It's kind of a little bit like building a wall. But then once you start curving inwards, these bricks really want to slide inwards. And so basically, what we discovered, what's key is, I think this is the go back button, is what happens here. Here with these vertical bricks. As you can see, these vertical bricks are stuck in the layer below, and they are a little bit like how I imagine book stands to be. So if you have book stands and then you have bricks laying there, once these horizontal bricks want to slide inwards, they kind of collide with the vertical bricks and they jam against them, and then they cannot slide inwards anymore. I'm going to show you on the next slide. You see a still of some of the analysis we're doing. So here, what you see here is, okay, the bricks are sliding inwards, but that is because we assume that the bricks are coated with Teflon. They have a friction angle of 0. If the bricks would be like Teflon coated, they would just fall inwards. But from the moment that we have a little bit of friction, which you see here, 10 degrees, and really in masonry, the friction between the bricks is 15, 20, or 30, so much higher than this. So from the moment you have a little bit of friction, these bricks kind of jam against the vertical bricks and kind of stay there. Then they press against these vertical bricks. These vertical bricks are stuck in the layer below, so they transfer the loads into the layer below, into that radial layer. Then that transfers through these other vertical bricks downward and all the way. So these forces are kind of transferred all the way down the dome. And we kind of checked, sliding of bricks, falling in of the different parts, and we found that actually you can build kind of curved surfaces like this. So that's all very well. This is a picture of Filippo Brunelleschi. That's all very well if you and we published about this, actually got a lot of attention. If you publish about things from the past that people are interested in, that gets a lot of media attention. So we were in La Repubblica, we were like in Smithsonian Magazine, everywhere. Anyway, but that's all very nice, but like, what do you do with that? What do we learn from that for the future? How can we use, we've discovered some algorithms on how we can construct without supports. I was thinking, could we use this with drones? Could we use robots? Or how could we do this? And I'm going to show you here, or I'm showing you here, a video of that SOM made, because we teamed up together with them to make a vault for an exhibition made out of glass bricks. That's not so amazing. But it is made, as you see, there is no support underneath it, right? So it's really humans working together with robots to build this system. And you might recognize some of these amazing vaults that have been built at the beginning of the 20th century. So the idea is to construct first a central arch and then build outward from there. Again, no supports. Only the robots that are positioning the bricks and holding the bricks into place. So glass bricks, have been used in design. And so robots are really great to work with because, well, of course, they can do repeated manufacturing, but also they can hold the brick for a very long time in position while we've used epoxy. The epoxy is curing. And they can also support loads. This is my PhD student. It's actually just starting I just started at Georgia Tech as an assistant professor. So we have epoxy. We also have wedges because, of course, the bricks are linear and the shape that we are doing, which is a compression-only shape, is curved. So we have to approximate this curved shape with these straight elements. Anyway, that was the beginning of an interesting adventure. It won some awards. And so in 2023, I was invited to present our work at the Venice Biennale. So this is an event where architects and designers and artists come together to present their work. And we were inspired by to do something with these algorithms that we had found in these Italian domes of constructing something without supports. We had learned from the robotic construction that actually, this is all great, but the robots cannot really give us any feedback about how the epoxy is doing. And so they would just hold things in place, but they couldn't really feel whether the brick is going down or not, because the epoxy is kind of a material that deforms. So we wanted to do something else, and we chose to do this in this garden here. This is the Palazzo Moro. In a palazzo, you can see it from the street. Many receptions are held there. Also, it's very visible from the terrace. And so we wanted to work within the restrictions of this garden. And this is a rendering, right? This is a rendering that SOM made of a complete compression shape that would be constructed without supports, that using that kind of herringbone pattern. And we had very little time to do this. So SOM did the design, we optimized the form finding, we did the brick patterning, we determined how the sequence of which brick should go where, we did the structural analysis. This is in Venice, so we also have to make sure it doesn't collapse under an earthquake. And of course, this, as you can see, this is a very complicated shape, right? This is very difficult if you work with masons. If you build a wall, you can say, okay, according to this line, so high, so many courses. But a geometry like this is very difficult to describe, rotate this brick so much, every brick is different. So how are we going to do that? Traditionally, people have used X, Y, Z coordinates, right? So if you look at architectural drawings, like the one on the left, people will describe the position of all these points in terms of X, Y, Z coordinates. That does not work so well if you're working with curved surfaces. For example, here on Earth, we don't talk about, I live in X, Y, Z. We actually talk about latitude and longitude, so two coordinates to describe. But that works well for spheres and for hyperbolic paraboloids. But to describe the geometry of something like this to a mason is very, very hard. So we kind of adopted a new technology, which is augmented reality. So basically, these are the goggles that you can put on your head, or also, I don't know, if some of you do Pokemon Go, you can actually hold your phone up and you see the reality, and then you see a little creature appearing. That creature is not there, but it's imposed on the real world. And so what you see here is our design floating in space at the office of the Italian contractor, and they are discussing how this thing could be built, right? So it's really wonderful so that the contractor, but also the mason on beforehand can actually see the structure, already identify what's going to be difficult, what is the construction process, because we can switch on and off layers, right? So we can determine first we do this, then we do this. Here it is floating in space, but of course we don't really want it to be floating in space on the side. So what you're seeing here, and actually what you're also hearing here, is now we're looking through the mason's goggles. So we've scaled this up, we've scaled it so it fits within the garden, and the mason sees where these bricks need to go. Right? I also have a lot of videos where there's a lot of Italian swearing going on, but I've chosen the one that doesn't have any swearing in it. But anyway, what you see here is you see this digital kind of, our model, and then you see the mason approximating that model. On the right-hand side, you see we're really not cheating, right? There's of course scaffold to bring the mason all the way to the top. It was also very interesting because we were curious whether the masons would actually adopt that kind of technology, because masonry is a very traditional craft, and here we come with like goggles and stuff like this. But it turned out that the mason, who's like a master mason, he likes gaming, and so he had already worn that thing a lot. And so for him, actually, it was very interesting to bring this very new technology that he actually knew very well into his profession. And so it really empowered him. So this is the final thing. This is my sister. This is the final construction. It was very lovely when I was in Venice. I have overheard, I'm listening to what people are saying, and some people said, oh, it has a really lovely kind of like craftsmanship to it. So you feel it's done by humans, but it is a very complex form. And so what you see here, I don't know if you see them, but here are those vertical bricks, the one that you saw in the Dome of Florence, right? It's the same pattern that we are using here to kind of be able to construct without having to support it. And here a view from above, so it has this lovely craft feeling to it. And it won the Innovation Award, so we were very happy with that as well. Okay, I'm going to come back now to the start of my lecture, where I started talking about storm surge barriers. And I feel tonight that is particularly relevant with Hurricane Helene coming up. So we've seen this. So this is a very typical way of protecting. We've seen you can just do the boardwalk, or you can do a stone wall, or you can put lots of rocks and hope that these rocks are going to protect you from the storm surges when they come. But as I mentioned before, I don't think the idea of using a lot of material, the idea of kind of really making a big physical barrier between these two landscapes is really a good idea. So my idea really is to use a big inflatable membrane that would be hidden below the boardwalk. And when the storm surge warning comes, this membrane would be inflated, and it would hopefully resist the storm surge. And then when the storms go, then it can be deflated again, and it can be stowed away below the boardwalk. So what you see here, this kind of barba papa thing, this is a big inflatable membrane. It is inflated. I'll go to the next slide. You see, for the ones that like engineering, on the right-hand side, you see how this would work. So here is the membrane. This is a cross-section. It needs a very big foundation, because otherwise it will lift up. If it is deflated, it can be stowed here. And what you see here is, of course, the water coming up. So actually, inflatables have been used to kind of shield off water. But they've been used in kind of more static conditions in rivers and things like this. So what is new here is the scale. We're looking at really complicated loading. Storm surge loading is both static, so the water rises, that's one thing. Then you have the waves that are coming onto it, so you have breaking waves onto it, and then you also have kind of the waves, dynamic load, hydrodynamic loading, the waves hitting the barrier on and off and on, and that then varies spatially. So of course, also very complicated. What kind of material is this? This is actually, we have very strong nylon textiles that can take these forces, but they have to be rubber coated, because if there are trees or very sharp objects coming, this has to be protected. So it's a membrane that's about this thick, consisting of a rubber coating and then a nylon on the inside. We are looking here at a diameter of, base length of 13 meters, but we're looking at diameter of 8 meters. We kind of did a case study for the Rockaway Peninsula, the one that I showed you the slide of at the beginning. And what is kind of challenging here is, a number of things. Well, the loading is challenging. I've explained that, right? There's all this complicated loading that varies with time, that is very high. varies with time, varies spatially. The structure itself is also very complicated because it's a rubber, so that is like a hyperlinear elastic material. That's very complicated. And then also this thing has to stay stretched all the time. So it cannot, it's a bit like a balloon, it cannot be indented because then it starts wrinkling and then it loses its structural function. So what you see here on the left-hand side is where we're doing some preliminary finite element analysis, and we see indeed if you inflate it, and this inflation can be with air or it can be with water, or it can be with a combination of the two. Water is not such a great idea because that then causes sloshing in the balloon. So we studied this under pressure of 20 to 40 kilopascals. And so what we see is when the water comes, like the structure moves a little bit to the right side. Here we have to be careful because we get some inversion of the membrane. So if the membrane goes into compression, that's not very good. And if you have water on both sides, it makes these bell shapes. And that is all kinds of behaviors that are documented in literature. But so what we found is, when we carried out further analysis, that these kind of barriers at that scale under that kind of loading will be strong enough, so the stresses within it are smaller than the strength of the material with some factors of safety. The balloon will deform, which is fine, but the water will not overtop, right? So it will like move sideways as you see, but it will not move so much that the water is going to go over it. And also there will be no resonance, meaning the kind of the way that the balloon wants to vibrate does not coincide with the resonance of the waves, because then we are again at that problem of like a resonance problem. What you see there on the right-hand side, I put that in because I think that's kind of interesting. We did also small-scale experiments in a wave flume tank. I don't know if you've ever seen that. It's a kind of a crazy thing. It's a long aquarium, maybe 90 feet long, where they have a paddle at the end and they start generating waves, and then you can put your tiny storm surge barrier model at the end, and then when it arrives at the end, you can take measurements and see what are the pressures on it, and then you can scale that up to the larger system. So anyway, so where are we going with that? So we are, so one idea is to really shield off, the coastline, or it could be maybe around critical infrastructure, around hospitals. But our idea is also like, what if we can kind of control the flow of water? So what if these inflatables are actually in the water and are now diverting the water to maybe more sacrificial pieces of land? This is something that they do in the Netherlands. There are lands that are designated to, if we're going to have a big flood, those areas, usually fields, are going to be flooded. We accept that, but at least these big inflatables could kind of direct the water towards the areas that you want, rather than just being completely surprised by where it's going. So, and this would be useful for what we call low-frequency large water events like storm surges and tsunamis. Okay, so I've come to the end of my talk. I hope that I've been able to show that, in my research group, we try to harness what I call the exceptional mechanics of these force model structural surfaces for a future-oriented, resilient, and sustainable urban environment. In my group, we study the interaction between these slender surfaces and the environment. We draw inspiration, I've shown you here, from biology and history, but I also work with artists and crafts, because obviously there are also systems developed, for example, in weaving that can be very useful for engineering applications. And we also develop all kinds of methods to study these systems. So we develop numerical methods, machine learning methods, graphical methods, and analytical methods to generate knowledge. And of course, I have to thank you for being a wonderful audience tonight. I need to also thank all my collaborators, my students, and my sponsors. So thank you very much for having me.
All right, get ready. We're going to turn on the lights. Want to prepare you for that. There we go. We have time for some questions. Raise your hand. I'll come by with a microphone. We're live streaming tonight, so we don't want any dead air, so don't yell out any questions, please. I'll come by with the mic. Yes. Hang on. Where was the hand? Okay.
Thank you. I just have a couple of questions. So the height of the membrane filled with air, you said
8 meters.
8 meters. So if storm surge, because of waves, let's say tidal waves, tsunamis, something like that, if they go over the membrane, then they're stuck on the other side until you deflate. Okay.
Yeah.
And then in addition to that, I know you mentioned the water park, and yeah, the Netherlands does a great job with, especially in UNESCO cities, to fund water parks to kind of absorb this water, and people love it when it floods.
Oh, yeah. Yeah, I mean, I'm from the Low Countries as well. Also, my country gets flooded. Flanders, which is the north of Belgium, and this is for the Low Countries not new. I have a painting from the 14th century where you see a dike breaking. There's also like cultural stories about this. So people have been in that part of the world fighting or learning to live with the water for a long time. And I think what's very interesting in the Netherlands, the people that are in the Ministry of Waterbouw, it's called, so water, the people that manage the water, they are highly revered. They are the most important people in the country. It's the most prestigious institution or ministry to belong to. So, they are, they're taking, if you look at the map of the Netherlands, like where there is land and no land, it changes often, and they decide, okay, this is now going to be flooded. They make sure that they can do that, but where the land is and where the land is not has changed many times under their. They manage it. They decide it. It's not the water that decides it. Yeah.
All right, we'll stay over here. We have an online. We have a question from an online viewer, James, who asked, how would these shells be scaled up for city building? For example, how would you apply the concept to multi-story buildings?
Yeah, that's an interesting one. So I think he's referring to the rigid shells because the flexible shells, the adaptive facades, I mean, they can cover entire skyscrapers and they can be applied to both planar surfaces and curved surfaces, but I think his question is probably about the rigid shells. So of course we don't want shells everywhere, like we don't need so many sports arenas and things like this. But what we do need, and this is really where this is going, what we do need is floors. Like as we are getting more people, we are going to build many more buildings. All over the world, right? Like maybe in some areas, for example, in Europe, people are more looking at reusing buildings and, what can we do with what we already have? But, we cannot ignore that in many parts of the world, many new buildings are going to be built. And so these kind of buildings are going to be residential buildings, commercial buildings, and there we need floors. And so some research, and actually I have not really shown this, but some research is actually focusing on using these curved surfaces as floors. Now, of course, you cannot really stand on a curved surface because, we don't want an office where the floor is like this, but you can use these floors and then, you can use these shells and then put a horizontal layer on them, support it, and that still makes like a very efficient and very cost economic system. So where would they go? They would go into the floor systems, the horizontal spanning systems, and they would be kind of the supporting systems for that.
All right, we have a question in the back of the room here on your right.
So as you probably know, countries in the global south are going to be most adversely impacted by the effects of, like, say, sea level rise. Are there ways to be able to use resources for especially developing countries to utilize that, and also utilize take inspiration from old traditional architecture techniques, same way you took inspiration from the Florence Cathedral?
Yes. So I am thinking partly in terms of materials, like, we don't all need to build in concrete and steel. I mean, there are many materials that are much more local and sustainable. For example, there's quite a lot of work being done on, for example, using earth as a material. For these compression systems, like the one that I showed with the glass bricks, I showed also in the Felix Candela shells, the stresses are very low in shells. So you can actually use very low quality materials. So you can use earth. You don't have to use super high concrete. Another material, actually some of my senior thesis students are working on this, is the use of bamboo. So that is a material, that's a grass that grows very, very quickly, is very flexible, is very strong. You might say, well, there are insects and there's fire, but you can completely treat it, so that is not a problem anymore. And in many parts of the world, bamboo is used as a construction material, but we can actually use it to span much larger distances, to make bridges with it, etc., etc. So that's, for example, another material that I think has a lot of potential. So yes, definitely we can learn from the way people have built forever domes and earthen structures and bamboo structures. Also, another material that is at the moment in Europe and also in the United States and Canada is being used more and more is wood for skyscrapers. They're making skyscrapers out of wood as a material, which is much more sustainable than concrete or steel. It's really, we've done some studies on steel, like steel, the embodied carbon of steel is just enormous. So, I think all we can do in materials that have much less embodied carbon that can do the same things as concrete and steel through good design, so through the use of shape, through the use of corrugations, folds, anything like that, topology, the way that you connect things, if you do optimization, all these kind of things can really help bring the forces down in the system, and then we can use these materials that have much lower carbon in them. Mm-hmm.
All right, we have a question on your left here.
Yeah.
I'm wondering if you've considered pairing up with folks with the ocean cleanup and all the plastics they're taking out of the Great Pacific Garbage Patch and bringing back to land and grinding them up and all the various things they're doing with all the different things. Mm-hmm. And they're looking for people who can use them, like Kia in their car manufacturing is using some of this. Mm-hmm. So I wondered if any of those materials from the trash could be used.
Yeah, that's a good question because, as I said, all these compression systems, they are very, the forces are very small, so we can look at a very wide range of materials. I don't really know for plastics in buildings whether there's also some kind of health concern, right? Because that's another thing. We live in these spaces, and like the paints, the plastics, the whatever. I don't really know whether that maybe poses a concern. But actually, I do want to kind of work with the people that clean up the oceans, because I also have some work, I didn't show it here, on nets, on how they behave. And so nets, they are great. If you imagine big nets that can kind of, sweep the oceans and kind of capture all that, all the trash. I have expertise on how to model them and how to design them so that they do what they need to do. There's not a lot of drag on them, et cetera, et cetera. But I didn't really show that here, but yeah.
Professor Adriaenssens, we have a question here up towards the front on your right. We're at the top of the hour, so let's do 2 more questions. Alan, I know you got a question, and there's one over here, so here you go.
Thank you very much. One question I had was, I'm an engineer, and pertaining to some of the more practical aspects of, for example, getting building codes to adopt some of these new techniques, and wondering if you've forayed into that realm at all, as to how that might how you might get some of this into some of the building code processes that sometimes take decades to change.
Yes, I have totally avoided that. So I used to, before I was in academia, I was in practice. So I am very well aware of the building codes. I've built large span roofs and bridges and all of that. But yes, there are, of course, the codes. And it is, as you rightly point out, it is very difficult to, even if you bring like a product onto the market, a new adaptive facade, it is very difficult. Well, yeah, it's difficult and a very long process to get your product on the market. It needs to do a lot of testing, and rightly so, because as I mentioned before, we are designing for a very long time. If things go wrong in our profession, if a bridge falls down or if a barrier goes, I mean, the consequences are terrible. I kind of scare my students with this. I teach mechanics of solids, the first class that they take when they enter our department, and I say that, like, I hope that you realize that, you're in a profession. If you make a mistake, it's like, you think maybe medicine, you're going to be sued if you're a doctor, but for a structural engineer, if you make a mistake and your design collapses, this is not just like one person, but it can affect many, many. So we have tremendous responsibility.
1981, the Hyatt Skybridge collapse killed hundreds of people.
Oh, yeah. So this is like, the worst nightmare, right? Like, civil engineers have enormous responsibilities because the scale is enormous, the time span is enormous, the consequences are enormous, the forces are enormous. So, but they still stay in my class. They still turn up, they still turn up on Wednesday, so that's good, yeah.
All right, we have a question here in the middle of the room.
Mm-hmm.
This is an aesthetic observation. This is an aesthetic observation with the Romans, and we had the dome, and with the Gothics there were lots of curves, and then in the later centuries everything has been right angles and rectangles. And I notice you're working with a lot of curves.
That's right. Yes, that's a very good observation. I think part of why at some point we were doing only rectangles is because building materials, glass is planar, steel is planar, wood is planar. But indeed, before we were working with curves. I'm now also working with curves. Some of my work, some people sometimes say, oh, it's more sculptural because it has this kind of curved. But yes, it might be visually interesting, but it is completely determined by physics. So actually, I also teach in the visual arts department where I work with a sculptor to teach students, that you can actually design things that perform, that have a function, but that are also, if you work with the laws of nature, kind of appear very natural. And I think that's what people also often say. It looks very natural, and it's yes, because we are used to seeing spider webs and shells, and nature does that as well. As I mentioned before, it uses very little materials. It uses form to achieve the things that it needs to do. So yeah, if you think about a snail needs to produce its own material to make its house. Imagine you have to do that. Has to come out of your body. So you're gonna make very minimal and make it really optimal. Anyway, yeah. So yeah, very good observation.
Professor Adriaenssens, thank you so much for a wonderful lecture.
Pleasure.
This is our 22nd annual Bartlett lecture. Can you believe that? And so, yes. Thank you so much for attending tonight, and please check out lindahall.org for a lot of future upcoming programs that I'm sure you'll be interested in. So thank you, and have a great rest of your evening.